Hello everyone. This is the 6502-based single breadboard computer that we built in a previous video of mine a few months ago, and in this video we'll be taking a look at how we can get 6502-based computers like these to play along with I²C devices like screens, accelerometers, temperature sensors, and thousands of other gadgets. While playing with breadboards is a lot of fun, it's not exactly meant to be a permanent solution. And as you might have noticed from the thumbnail of this video, it's gone through a bit of a transition. A printed circuit board is way more convenient, so I thought I might as well go ahead and make one for it. I'm a huge fan of making things using recycled parts, and by making something that's useful in 2023 out of these old chips and sharing an easy-to-make design, it's a great way to keep the old chips out of the landfills and create innovative solutions without buying new chips for hobby projects. Basically, we take something old out of the waste stream and at the same time avoid buying and eventually scrapping something into new waste. A complete win-win. If you're following along at home on a breadboard, don't worry, you can still do that since we'll still be using the same integrated circuits. And of course, the project is also 100% open source, so you can easily send the Gerber files off to a board house and make your own. Links to the project in the description. The PCB I designed is pin compatible with the popular Arduino Uno that hobbyists and many a hacker will already have a strong familiarity with. Of course, it's not in any way associated with the Arduino company, and I think that'll be clear if I call it a 6502. Even though there's a big difference between the 6502 computer and an Arduino, this does mean that many, if not most, shields and add-ons for the Arduino will also be compatible with our little computer here. Of course, the main IC on the Arduino Uno, the Atmega 328P, has quite a few more features than the 6507 plus 6532 combination we used on the breadboard. But even though it doesn't have analog pins, needs an external clock, and the Atmega 328P is generally better in every way, it's also over 30 years newer and hides everything away in a single package. And that makes it harder to visualize what's actually going on, and why would we want that? So on the plus side, we still get to play with integrated circuits that were developed close to 50 years ago, and we can still use it to play with many of the modern gadgets. Best of both worlds in my book. And that brings us to the topic of this video. Back in the 70s, most additions to a 6502, 6800 or 8080 based system would interface straight to the 8-bit data bus along with a few address pins, but as you can see, none of the gadgets I have here seem to have more than a few pins. But wait, that 16 by 2 LCD screen has way more than the other things, you might say. If you've seen Ben Eater's 6502 videos, that's a reasonable thing to assume, since he goes into great detail using it directly on the 8-bit bus with a couple of control lines. But instead of doing it that way, on the back of this one I have a little 50-cent module that takes the pin count all the way down to 2 signal lines like the rest. So how does that work? Well, back in 1982, Philips, who by the way spun off to NXP Semiconductors in 2006, got pretty fed up with having to make huge, expensive BIP40 packages for even the simplest of features, and decided it was time for a better way for chips to talk to chips without needing 8 data lines, read-write lines, and a ton of address decoding just to read a single register. What they came up with was the Inter-Integrated Circuit, or I²C bus. A 2-wire interface that does it all. The I²C bus has tons of features and many have been added over the years, but the main selling points are that it only needs 2 wires besides power and ground, and unlike SPI, we can put a lot of stuff on the same bus without a chip select line. It even lets multiple controllers use the same bus and even at different supply voltages. So if we take a closer look at this little monochrome OLED screen, we'll see it only has power, ground, a pin called SDA, and a pin called SCL. In other words, a data pin and a clock pin. Oh, and it looks like I forgot to solder the PCB, so while I do that, we can talk a bit more about how I²C achieves its magic. If you've seen the video where I make an adapter to convert the PS2 keyboard protocol to the PCXT protocol, you'll see the similarity that the I²C bus is also open collector and takes advantage of the fact that anything on the bus can pull both lines down to ground without the risk of damaging anything. But the only way to make a line go high is to release it and let the pull-up resistor on the lines do their job. This is usually also the speed limiting factor for I²C, and if you run it at high speed, you might have to add extra pull-up resistors to let the lines go high faster. I'm not going to talk about the more complicated features like bus arbitration, clock stretching, 10-bit addresses, fast modes, and such, but I can promise that by the end of this video, you'll have a pretty good idea of how I²C works at the most basic level. And if you want to learn the slightly more complicated stuff, the specification is actually only 60 pages long. In a few moments, we'll start writing some code, but first let's make a plan for what we're trying to accomplish while I finish soldering the PCB. An I²C transaction consists of a minimum of a start condition, including an address, along with a read-write bit, an ACK or NACK from the target, and a stop condition. A start condition is any time the data line, SDA, goes low while the clock line, SCL, is high, and a stop condition is any time the data line goes high while the clock line is high. This has the consequence that the data is only allowed to change during a transaction while the clock line is low. Otherwise, we introduce false start or stop conditions. Technically, the whole data byte is optional since we can send a stop condition after the first ACK bit. Why? Let's say we want to quickly scan all the addresses to see what's listening, so we don't want to waste time sending or receiving data we don't need. In that case, we can just send a stop condition after we get the ACK or NACK. Since an address with no response would leave the ACK bit in the high state, a NACK is a 1 and an ACK is a 0 bit or a low. Usually, we would start with a write transaction indicating the register inside the I/C we want to read from or write to. Some I/Cs will let us keep writing bytes after we send the register we want to write to, while others will require a repeated start condition without a stop condition first. It all comes down to the datasheet of the specific device we're trying to talk to. But even if we can't program one routine that fits everything, we can write a few routines that we should be able to combine into transactions that make sense for the specific I/C we're trying to control. After assembly, it looks like the 65 Arduino has no problem running the exact same code as the single breadboard computer, so it looks like it's ready to talk to some I²C devices. You'll notice the LED blinks a lot slower on the 65 Arduino, and that's simply because I moved the LED to the highest bit on the port, DRB pin 7. Even though I did move a few pins around for the PCB design to make logical sense for the Arduino-like pinout, it still blinks the LED on port B pin 7, aka Arduino pin D13, since the code increments the whole port on every clock tick. I put the user button on port B pin 6 because it's easy to check with the bit instruction. The pinout you see here on screen is basically where I routed the power signals and the I/O ports of the 6532 Riot. And since I had plenty of space left over, I decided to add a new header that's usually not found on an Arduino. We already have two other places on a typical pinout to access the I²C bus, but I thought it would be nice to have a dedicated header for the cheap and common monochrome OLED screen with a built-in SSD 1306 screen controller. So why don't we start out by writing some 6502 assembly code for a basic I²C transaction and then move on to write a little minimal library to control the screen. This is the code the way we left it after we finished getting the 6502 single breadboard computer to blink an LED using the 6532 timer and change the frequency using a button press. A pretty good 6502 Hello World example. This time we'll dig a bit deeper and I'll assume you know at least a tiny bit of 6502 assembly code syntax. So if you don't, you might want to check out my previous video first, or if you're a complete beginner, maybe Beniter's 6502 videos. They're awesome. Since we can assume we want to use the same I²C address several times and probably have a few different devices connected at the same time, we'll need a RAM location for the address. And maybe a few other related things like the byte we're sending and receiving, so let's assign them a spot in RAM, but also make them easy to relocate. With the amount of bit juggling we'll be doing here, our code will be a lot more readable if we assign the pins we'll be using to a constant, as well as their inverted bit mask for when we want to clear a bit. Of course, I could also write macros to do the bit flips, but since macro syntax can vary between assemblers and also makes it hard for beginners to see where the line goes between what's a 6502 instruction and what's a made-up macro instruction, I will spell out all the instructions. The code will be a little less compact, but also a bit less complicated. The I²C address notation is one of those things that haven't been specifically spelled out in the specification manual. So on some devices, you'll find the 7-bit address noted as the byte you actually send, including the read-write bit, while others note the address before it's been shifted left. Of course, the latter is the most logical way to do it, since that shows us the literal value of the address bits themselves independent of other things, even if we have to shift it 1 bit left before we send the address byte. It does mean the notation on the back of this SSD 1306 module is incorrect for our code, and the address we'll need to use is half of that, 3C hex. In practice though, both ways are easy to handle as long as we're consistent. If we just assume we have the read-write bit in the carry flag, we can combine it with the address using a simple rotate left, shifting the 7 address bits to the top and the read-write bit into bit 0, all ready to send. Remember to set a specific bit in either the output register or the data direction register to a 1 without affecting the rest of the register. We OR the register with the bit mask of the bit we want to set. And if we want to clear a bit without affecting the rest of the register, we AND the register with the inverted bit mask of the bit we want to clear. Like I mentioned earlier, I²C is an open collector protocol which requires that all devices can set their outputs to high impedance, essentially disconnecting them from the lines, letting them get pulled high if nothing else is driving them low. This means we can't just set the line high when we need it to go high. Some modern microcontrollers have high impedance capable outputs, which means they can either drive the line high, low, or essentially disconnected from the bus. The Rockwell 6532 we're using for our GPIOs does not. When the line is set to an output, it either drives the line high or pulls the line low. If we drive a line high while something else is trying to pull it low, we're not only going to lose, we'll most likely lose the ability to ever pull that pin high again, if not the whole chip. We're not completely out of luck though, since as far as the bus is concerned, the line is high impedance and essentially disconnected if we just set it to an input by setting the pin number to a 0 in the data direction register. To get a low or a high voltage on the line, we either set the data direction register as an output to pull it low, or set it as an input to let it get pulled high. Since the data register keeps its value when switching from input to output, we can just leave it at 0 and just toggle the direction register bits. Since the clock pin is conveniently located on pin 0 of DRB, we can even use the increment and decrement instructions to flip the clock pin in a single instruction, as long as we keep track of what state it's supposed to be in. For the SDA pin, we still need to OR or AND the direction register to change states. Slightly confusing when setting it to a 1 means low and setting it to a 0 means high, but I hope the reasoning came across. If not, feel free to ask in the comments. Now that we have our start condition, we can move on to sending the first byte containing the address and the read-write bit. Since sending a byte is a function we'll also be using separately, and we're doing exactly the same thing when sending address bytes and data bytes, we can start by making a new entry point and ensuring SDA is low and get ready to loop 8 times, once for each bit. For the loop, we simply shift the next bit into the carry flag, and if it's set, we set the SDA pin as an input, letting it get pulled high, and if it's clear, we skip that part and set the SDA pin to output forcing it low. You might have noticed I incremented DDRB twice in a row when coming from the start condition, which would break things, but I put it there since we get a slightly more even loop, so we don't make a too short clock spike. The fix is to skip the first clock change. After that, we get ready to clock in the ACK bit, set the SDA line to input, and clock in the ACK bit. If we get an ACK, we set the carry bit. If not, we leave it cleared, and that's all we need to do to send an I²C byte. Eventually, we also need to read bytes, so to do that, we need a separate function. It has exactly the same structure as sending a byte, except we rotate the bit in, and for now, we just send a NACK after receiving a byte. You might think a not acknowledge is weird when we receive a byte just fine, but in this case, it just means don't send any more data, since we're only reading a single byte at a time with this routine. The last thing we need for a complete transaction is the final stop condition, which is simply setting SCL high before setting SDA high. Oh, and it looks like I mistyped the label. That should be it for our basic I²C routines, but if we plugged in a module at this point, of course it wouldn't do anything, but also we might actually fry it and release the magic smoke. Like I mentioned earlier, it has its own header and it plugs in rather nicely, but at the moment I'm not going to try that with the power on. Since DRB is still initially set as output and cycles between 5 volts and ground, like the breadboard version, now is probably a good time to fix it so both SDA and SCL are initialized as inputs before we plug in the screen with the power on. Of course, we also have to write some registers in the display to make it do anything at all, but many I²C modules have 5 volt tolerant power pins and some protection, but they still might not be able to handle 5 volts straight to the data and clock pins. If they're set as inputs, we limit the current and improve the chance of survival, even if the chip in question technically isn't 5 volt tolerant. It's also more than a good idea to check the datasheet if you're not 100% sure. But if we look at the datasheet for the SSD 1306 I²C in our module, you might be surprised to find that it isn't actually 5 volt tolerant, like it's advertised on most markets. Thankfully, that's not just exaggerated marketing, but down to the fact that the modules usually come with this little XC6206 SOT23 regulator that takes the input voltage down to a reasonable level. But since there's no such thing on the other lines, 5 volts with enough current on the data and clock lines might damage the IC if we're unlucky. After that little side quest, we better get back to writing some code that'll actually make the display do something. First of all, let's fix it so bits 0, 1, and 6 are initialized as inputs, so we don't risk frying anything, and our I²C code will actually work. Just so we don't forget later, let's change our button reading code to use DRB pin 6 instead of the top bit of DRA. Since the bit instruction puts bit 6 in the overflow flag, we use the branch overflow instruction instead of branch plus. This also inverts the logic. When we press the button, it blinks faster instead of slower. Since we're using the other bits of register B now, we can't use the increment instruction to toggle the bit anymore, so what we need to do is to read the LED bit and check if we're toggling on or off. Again, we can read the LED on bit 7 with the bit instruction, since that'll put the bit in the sign flag. A thing to note is that the 6501 has the LED hooked up with the cathode connected to the pin, since the 6532 Riot can sink way more current than it can source. Now that our Blinky code is fixed, we can get back to what we came to do. Let's get the display running. To initialize the SSD 1306 I²C over I²C, we have to tell it a bit about the module it's part of. It doesn't even know the resolution of the display itself. Kind of like a person who doesn't know anything about themselves when they wake up in the morning until someone tells them. Don't we all know a movie where that happens? So what we have to do is send a series of commands 1 byte at a time. Since we don't want to clutter the top of our code too much, let's get the display address ready and throw the initialization into a subroutine a bit out of the way. Fortunately, we can do all of this in a single I²C transaction, and to make it easy to change in the future, we should put the configuration data in a table and load it from there. We could make the initialization a bit faster and get rid of the compff instruction by keeping track of how many bytes we're sending and write the table in reverse, but we don't have to, and it's probably just a few milliseconds. I'm not going to explain the initialization commands in detail, since they're basically the same as the example in the app note that's included with the datasheet, except I do try to increase the refresh rate of the display a bit to reduce flicker on camera. With the initialization ready, that should actually be enough to make the screen do something. So let's grab the ROM and burn our code. The charge pump and voltages in the display take a bit longer to settle after a cold start, so we need to press the reset button to resend our initialization code before we'll see something. We can fix that later by putting in a delay before we initialize the screen. And voila! A screen full of random dots. If that's not what you expected, I don't blame you. Since the RAM in the display doesn't initialize to any particular value by itself, and we're not writing anything to it yet, the display simply shows the random data in the frame buffer RAM. If we disconnected power long enough and turned it on again, we'd get a different pattern. The display is a bit dimmer and flickers on camera because the refresh rate doesn't match my camera. It doesn't do that in real life, so I'll try to adjust the camera to give you a better view of the random dots. So at this point, you should have a good basic understanding of how the I²C protocol works and even how to use it with a 48-year-old CPU design to display random dots. But of course, displaying random dots isn't all we're trying to accomplish here, so in the next video, we'll take a look at how to make a font so we can display some text on the display. Eventually, I also want to show how we can use a software serial protocol on the 65 Arduino to display text and load software from our computer without needing a programmer to burn the ROM every time. I hope you enjoyed the video, and if that's the case, I'm sure you know what to do, and either way, I'd love to hear what you think in a comment. Thanks for watching.